Okay, it looks like it's okay, so I continue. So now we're going to talk about a little bit about model class. Now with respect to model class, there are many ways to classify things. In this particular case, I'm just going to classify them as follows. The model could be let's see, again, try to stick up to the notes that because there's a set of notes here that I'm going to post for you guys to have, which I've prepared. Okay, so we can have a model in which the spatial domain is completely finite. For example, let's say this building, where following the arguments made previously, perhaps I would analyze it if it was being excited by dynamic forces that were horizontal. It would likely be just doing this kind of thing. Most of the inertia will be horizontal, and that would have, let's say, 4 degrees of freedom. This system has a finite number of degrees of freedom in the model, of course, and the domain is limited, right? It's finite. Now, another thing is, notice that I put these foundations here, right, as being fixed. That means that I separated the building from the rest of the world, because of course there's the planet here, right? So I just said, you know what? That point of this structure is connected to something else, right? The planet is another structure, but I don't care. That point, I'm going to say, it doesn't move. All right. Now, that may be fine, but there are other problems in which you may not be able to say that. What if this support is here, right, are on a soil that is not really something that you cannot, that you can assume doesn't move? So it's kind of hard to know now where is it that this model finishes, right? So I may be, in a certain sense, considering soil. I may consider a model that is semi-infinite, because I may, and there's ways to handle that, I may consider a structure that is actually connected to a semi-infinite domain. Semi-infinite in the sense that it doesn't exist above this line, but it exists forever in the other direction, to consider the soil. I may also have situations where I may want to treat it as semi-infinite, which are really not semi-infinite, but they're so big. Well, actually, this is not semi-infinite either, because the planet finishes at some point. So I guess it's the same thing. I may have a dam with water, right? Well, this reservoir finishes over here, but that might be a couple of miles that way. Now there is an earthquake here, and I'm trying to investigate the pressures of the water on the dam and so on. I may be able, it may be appropriate to just model this thing as if this water layer actually went on forever, right? So this is the same as the problem of the structure with the soil beneath. This is semi-infinite domain, right? I can have also, so I have a limited domain in which I cut the boundary. I have a possibility of having a semi-infinite domain. And in some problems you might have an infinite domain, in the sense that, I don't know, you might have, you might be wanting to investigate, let's say, the effect of an explosion inside a mine or something like that, right? So, you know, you can assume that your dynamite or whatever it is inside a domain that for all practical purposes is infinite in all directions, right? Three-dimensional. And so the problem may be, the one that we typically handle, right, is the one that is finite domain, because what? We make simplifying assumptions as to how our structure is connected to the rest of the planet, and we say, well, you know what? We know how it is, and we assume that we know exactly what happens in those connections, and then we can throw the rest away. So this is the typical one finite domain, but we also have the cases of finite infinite, semi-infinite, the dam, or the soil structure interaction problem, or we also have the infinite one like this, okay? Next, in this class, by the way, most of the time we're dealing with the first class, which is models which are just finite. Now we have linearity. So what about linearity? I erased it a little too early, but by linearity we simply mean, of course, that if we have some set of loads and the response is QA as a function of time, and the same structure is subjected to some other set of loads, 2, and the response is QB, right? Then essentially we mean that the response of the structure to a load, which is load 1 times alpha plus load 2 times beta, is a response Q, which is simply alpha times QA plus beta times QB, right? So this is what we mean by linearity. Now, linearity holds as an approximation in a large class of problems that we're interested in. It doesn't hold all the time, right? So one has to be aware of those cases where it does not hold. Linearity may not hold because the deformations are too large. For example, these loads may produce deformations that are too large, and so it's not true that the addition of the two of them is still the same thing as, the application of them together is not necessarily the same thing as their application separately. And so geometric changes might affect the material, may be incapable of taking load 1 and load 2 both together, and so on. So nonlinearity is certainly possible, and it can come from material or from geometric reasons. We will deal with nonlinearity a little bit here, but not very much. It's a side issue, but we will mention it here and there, and then I think I have in mind to do something for the first time in this course with a little bit of nonlinear systems formally. Okay. Okay, now time invariance. In the notes there is a little bit more formalization of this. Time invariance. By time invariance, what we mean is that the parameters of the system are not changing. So, for example, when we say our system has a mass, right? Like this, for example, right? Let's say the single degree of freedom that we looked before. I wish this thing was darker. Same thing. Right? Again, the notes have more formality, but at this point we would say this is our typical case. If we had a situation where the mass was itself a function of time, right, then this is not time invariant, right? This is the typical case, time invariant. Now, under what conditions can we have problems like this? Well, in structural engineering, we often don't have them that much, but you can certainly see that, let's say, in the model of a plane, the mass of the plane when it's taking off from Logan Airport going to Rome, right, is not the same that when it takes off that, 3 hours in flight, because there's a significant amount of fuel that has been used. So if you are modeling the behavior of the plane to know what's going on, then obviously, the mass that you use has to be a function of at which time you're looking at, right? Now, it may be that the variation of the mass is slow compared to the dynamics that you're interested in, and therefore, in that case, you would be able to say, here is Rome, here is Boston. I'm interested to find out over here, what is going on if I have a certain turbulence and so on. Well, at that time, the mass here may be mb, right? Since you're interested in finding the behavior of the plane for, you know, I don't know, 5 minutes, it may be that the mass doesn't change so much during those 5 minutes, and so this becomes the mass sufficiently close for the analysis. In other instances, that might not be the case. The mass may be very fast enough so that you cannot treat the problem as having just a single value of the mass. In that case, you don't have a time invariant problem, you have a time variant parameters, okay? For the most part, we are dealing, actually, I think not for the most part, in all the problems that we will have in this class, we have time invariant properties. I already mentioned nonlinearity, so now let's talk about a little bit about damping. Again, let me check one thing with time left. Yeah, we still have time left. So let's talk about damping a little bit. If we look at a single degree of freedom, again, you know, if we put mq double dot plus kq equal to pt, that has no way to, actually we don't even need pt. Let's just say no load. So if we just look at this system with a spring and a mass, right? Mass m, spring k, then if this system is set up from some initial condition, let's say at q0 equals to a, right? So you move the system over to here, right? A distance a, and then you let it go, that system would vibrate forever, right? It has no energy dissipation. You haven't described how the energy dissipates, but we all know that in reality the system will in fact stop. So there must be some mechanism that is getting rid of the energy there, right? Now, we normally assume that the mechanism that removes the energy from the system, which we refer to as the damping, happens to be of the viscous nature. Meaning, by viscosity, that we assume that the damping is, that the damping force is proportional to velocity. So we typically write this thing like this, and we add this element, which is a damper, right? Such that if we look at the free body diagram of the mass again, right, it has the load PT, it has now the spring, which happens to be pulling back with KQ. We have the inertia, which we put in the opposite direction, as we said before, mq double dot. And then we throw in this dash plot. And this dash plot is to oppose the velocity of the mass. And then we can show easily that this thing will dissipate energy. Now, the fact that we make it proportional to the velocity is why it's what justifies the name viscous damping, right? But it is very important to keep in mind at all times that this is an idealization in a real structure of a number of mechanisms that are not particularly well characterized. We just simply have to represent the ability of this, not the ability, the empirical observation that the energy finds its way out of the system when we make it vibrate. We make anything vibrate and it stops. Now, why it stops? Of course, it stops because there is air resistance. It stops because there is friction. It's between parts. It stops for a bunch of reasons, and depending on the structure, it could differ. But it doesn't really necessarily, well, in most instances, is not because there is a damping dash plot that is proportional to velocity that stops the system. So what we use is something simply equivalent, or that we hope to make as equivalent as possible to the actual dissipation. We do not really mean that the damping in the structure is viscous. Now, there are some cases where you can have viscous dampers that are truly viscous dampers. For example, the shock absorber in a car may be an actual dashpot, right? In fact, if you have a container with some sort of a liquid, right, and that container has a small hole from where the liquid, well, I should have done it horizontally so it doesn't look so weird. But you know, you have a container with a small hole, some liquid inside, and the thing that can push it like, I'm sorry, that can push this way, right? It's clear that if you want to make the liquid, the fluid, if you want to make the fluid leave this container, then the force you have to use to make the fluid leave fast is a lot bigger than if you make the speed at which the fluid leaves is slow. So we would say essentially that this is of the, you know, it's CQ dot type of force. That is, if you want to make this thing go fast going out, then you need a lot of force. If not, you need less, and so on. So sometimes you do have exactly viscous dampers. Another one is like, you know, the stuff that we use on the top of a door. When you open a door and the door comes back, and the door, you know, it comes back, but it comes back slowly. There is the mechanism that it's on top of the door is actually something of this nature most of the time. So it's a viscous damper. In fact, if you try to push the door quickly to close, you find a lot of resistance. If you let it close by itself, then the resistance is much smaller, right? That it's going like that. So now damping, again, so one thing to keep in mind at all times is that whenever we're talking about damping, and that's something that is often forgotten in dynamics by some people, and we're talking about damping, and we say that the damping is of the form CQ dot, viscous damping, it's important to keep in mind that, let's say PT, that this is just a model to capture dissipation. It doesn't really mean that we think that there is viscous damping there. Now, one thing that it becomes immediately obvious here is that you might say, well, why don't you use, like, maybe CQ dot square was better? Well, maybe it is better in some cases, but you can see that if this is Q dot squared, or the square root of Q dot, or something else, whatever, some other thing, the equation becomes much more complicated to solve. So one of the reasons, in fact, one of the very important reasons why we use viscous damping CQ dot is because it makes the mathematical solution of the differential equation that results simple. Okay? Now, that means that in selecting the C, or the equivalent, sometimes C is a number, sometimes it's a matrix, depending on whether we're dealing with one or multiple degrees of freedom. But what we do then is to select C such that the rate at which the structure tends to dissipate energy from our observations more or less is correctly captured. Okay? Viscous hysteretic. I think I want to add a few commentary. Let me see what they are from the notes. Well, there's a long discussion in there in the notes. I think I'll let you read it, and I will just focus here on the more conceptual issue of clarifying the distinction between viscous damping and hysteretic damping. If you write the equation of motion like this, let's say you take a single degree of freedom system, and then you say over here there is some damping force. You don't commit, and then you say KQ here, and then you say PT, right? You could do that. Now that means that you could say that the damping force is equal to the applied load minus the inertia minus the resistance, right? So now I have something here that goes into some mathematics that requires the Fourier transform and the Hilbert transform and so on. So I'll skip them. But what I want to say is this. Imagine for a thought experiment that you could do this. You're in an experimental nature, right? So you go to a system and you somehow magically are able to measure, you know the mass, it's a single degree of freedom, you're able to measure the acceleration, you know the stiffness, you're able to measure the displacement, you know what applied load you have, you do something, and of course you just make this subtraction, right? So you find the damping force. Now, so experimentally you could find the damping force. Now, you could test, is the damping force approximately proportional to velocity? You could ask that. If the answer was yes, you'd say, oh, well, the viscous model seems pretty good. I could probably say that the damping force is, approximately some constant times the velocity. But what we find when we actually do that is that that's not normally the case. That we often make PT simple by making it a harmonic load. Okay? I'm going to erase because I don't have much room. But imagine that PT was harmonic. That is, that PT was like this. Just to make it real easy, right? And this is the time. And then you can do this calculation. Now you would say, well, I'll try another PT, much faster, like this and so on, right? So that I'm applying the load faster, the response is going to be faster and so on. So when we do this kind of test, what we find is that the damping force is really not proportional to velocity in the large majority of structures that we're interested in. Now, what we find is actually that it is sort of independent of velocity, okay? And an idealization of a damping force that is independent of velocity is what we call hysteretic. Okay? Now, hysteretic damping, we will come back to it later in the class. But I am going to right now limit myself to equation, and there's a bunch of derivations in the notes, but I'm going to limit myself to note that you eventually get to this. M Q double dot minus N H of QT plus K Q of T equals P of T. So the hysteretic model the viscous model is MQ double dot plus CQ dot plus KQ is equal to PT. Okay? So the viscous model on the right side, MQ double dot plus CQ dot plus KQ is equal to PT. This is damping force is proportional to velocity. The hysteretic model, damping force is not proportional to velocity, is proportional, because this is a constant, is proportional to this. And this is called the Hilbert transform of Qt. Okay? So if we use hysteretic damping in our models, then in the time domain at least, the equation of motion would have the damping term as being proportional. There's a negative sign, but that doesn't really matter. Proportional to the Hilbert transform of the displacement Qt. Now, what is the Hilbert transform of the displacement Qt? Well, the Hilbert transform of any function is the integral from minus infinity to infinity of the function. So let's say of the function ft. Why do I have to use st? Let me just use Qt. Q tau t minus tau d tau, and if I remember correctly, there is a 1 over pi in the front. Let me remind myself. Where are you? Yeah, 1 over pi. Yeah, and there's a 1 over pi here. So this is the Hilbert transform of Qt. Okay? So the Hilbert transform of Qt is a function of time, which is given by this expression. Now you can see the tremendously more complex nature of this description of the damping force than of this one. This one says the damping force at time t is just the velocity times a constant. This one says the damping force at time t is some constant, but you got to calculate this integral, and this integral depends on what? This integral depends on the history of the displacement, and now you say this doesn't even make sense, because it says that it depends on the history of the displacement for all past and for all future of the displacement. That means that if the true displacement is this, Q as a function of time, and this is time, and this is the damping force, hysteretic, then that means that at this time, if you wanted to know the force here, what is it? You would have to do this integral of Q of tau, t minus tau, right? So that means from minus infinity to infinity. So that means it depends on all the past of the Q as well as all the future of the Q. Now the damping force at time t cannot depend on all the future because the future hasn't even occurred. So we know that the hysteretic model cannot be exactly correct, right? However, if you look at the integral, you see that in the denominator there is t minus tau, right? So that means this is what we call, when tau is equal to t, this is a 0 and that thing goes to infinity. So this integral is called the principal value of the integral and so on. But you can see that as tau is very close to t, so the point is that all that really determines that integral is what's happening in the very near vicinity of the time t that you're looking at, right? So as you're doing this integral and tau is going and changing, when tau gets very close to t, this becomes very small, and all that matters really is just what happens around t. However, it's still symmetrical with respect to t. So the future just in front is as important as the future just in back, right? Interestingly. So this model is what we refer to as non-causal. And we know that real physics are always causal, so meaning that, you know, the effect has to be preceded by the cause. You cannot have something now depend on something that will be happening later. Yet, the hysteretic model does provide, in certain circumstances, does provide, when you confront it with test data, often results that are quite quite good and in many circumstances. So, but in the time domain, to solve this equation in the time domain, it's impossible to do it without iterations, because you want to find Q, but the forces here depend on the Q for all times. So essentially there is a need for iterations, and I think I prepared a little program to actually do it, to illustrate the difference with when we approximate this with the viscous model, right? So one of the things we will learn, but I will have to do that when we come back, when you know, in the lectures in class, because it requires a little bit more concentration than I would like to put here on a YouTube tape. But the point is that we could actually take a particular example and assume that the damping is hysteretic, get the exact solution of this equation, and then we would be able to see what happens if we use a good, quote-unquote, good value of C, and how close can we make these two responses be, right? And of course, if we had to do it one at a time, that'd be bad, but we don't have to do it one at a time. We can actually come up with rules on how to select the values of C such that the match between the viscous model and the hysteretic model, assuming this one was pretty good, is quite accurate, okay? Oops, somehow I noticed that by mistake I erased the things that was left on the right hand side that was guiding what I had to say, but the last point, yeah, I do have it on the notes over there. We have two last things to comment on. One of them is loads, types of loads, right? Now, we can have loads that are, you know, deterministic. That is, we happen to know the history, right? So P sub T is known. We can have loads that are stochastic. And actually, then we can get into philosophy here, because the loads are the loads. So it's not like, okay, hey, look, this is a stochastic load or something. I mean, what we're talking about is our knowledge of the load. So it may be that I actually have deterministic knowledge of the loading. That is, I can measure it, or I can see it, or I'm the one applying it, or whatever, right? That means it's a deterministic problem. It may be that the loading is stochastic in the sense that I have no ability to know what it is at every instant in time, right? For example, I am trying to design the plane wing, oops, excuse me, I'm getting a call. Let me pause this and answer it.